All right, so proportions in similar triangles. These are just some weird properties of triangle. Not all triangles either. Most of this stuff deals with triangles, but there's even one of these that doesn't even involve triangles. But some weird proportionality relationships that make sense. I mean, they just sort of are common sense things. So here's one of them. If we've got a triangle and a line passes through the triangle, intersects the triangle, parallel to one side of the triangle. Everybody see where we are here. We've got this line that's passing through the big triangle QRS, and it's cutting the triangle, it's intersecting it at U and T, right? Does that make sense? So that segment UT is parallel to segment SQ, right? What do you suppose happens then? Well, I guess you can see right here what happens then. What do you think happens? Are there any proportionalities that you think get set up there? I mean, we could always break this down into a small triangle and a big triangle that are nested, and we could come up with these proportionalities. But there is a proportionality that comes up here. How do you suppose that these segments, that the segment RT and QT are related to segments RU and SU? What do you think? What do you mean they're equal? Okay, now similar is almost the right word. We can set up a proportion here, right? So we could say that the ratio of, if I look at the top segment that's been cut at T, right? We've got the segment QR that was the side of the big triangle. It's been cut by this intersection, this other line here that intersected the triangle parallel to one side. And it's cut both of these sides into two segments, a big red one and a small blue one, right? What we know here is that big red to small blue equals big red to small blue. Okay, so we get that proportionality. And you can just sort of see that you'd have to have that, right? So in other words, each of the two sides of the triangle that's been cut has been cut proportionally, so that the two parts that are formed are proportional. Okay? Make sense? Okay, so we also have a converse to that. That works in reverse. So we also know that if we get this triangle that's been cut like this, and let's just say that we know, or we've got numbers up here so we can see that the ratio of RT to TQ is equal to the ratio of RU to US, then what do you suppose that says about those two lines? If this line right here has cut this triangle proportionally, how must it be related to that side? What do you think? It's got to be parallel. Yeah, so we can read that one either way. The converse is also true. Either we can start off like we did in the first relationship. If the lines are parallel, then we know that the segments that those lines cut have to be proportional. Or, so we can start off knowing the lines are parallel, or we can start off knowing that the segments are proportional, which shows us that the lines are parallel. Either way, works both ways. Okay, so what about this guy? In the diagram, we're told here in this picture that AB, segment AB is parallel to segment ED. So let's mark that on there, right? So we got this guy is parallel to that guy. Okay, they give us a bunch of segment lengths, and they want us to find, the question is, what is the length of EC? So let's call that X. That's the one we're looking for. So everybody stare at that for a second. Can you come up with a proportionality that we could solve for X? Okay, right, so we know that these two lines, this line has come in and it's cut through the triangle parallel to one side, so it's got to cut the two sides proportionally, right? So top over bottom equals top over bottom, right? Does that make sense? So 4 over 8 equals x over 12, right? And then we're experts at solving proportions. What do we do to solve this? What do we do? If I want to solve a proportion like this, what do we always do to solve proportions? Yeah, cross multiply. So I'm going to get 8x equals 48. Good. And so you would give me the answer. So x equals, if I divide both sides by 8, x equals 6, right? Okay, good. Good, good. All right, what about, oops, wrong one. Never mind. Okay, what about this one? Yeah. All right, so given the diagram, determine whether segment MN is parallel to segment GH. So we stare at that segment. You can come up with a way of doing that. How could we determine if those two segments are parallel? What do you think? Somebody raise your hand. Somebody help me out. What could we do? What do you think? Blake?
Make sure they're proportional.
Okay, good. So we got to make sure if this segment right here, you know, this line MN that's cut through the triangle has cut it up proportionally, then we know that the lines are parallel. So we'll just check and see if they are proportional, right? So is 56 over 21 equal to 48 over 16? Well, we can find out. And it turns out that they're not, right? 56 over 21, let's see, 7 goes into both of those. 7 goes into 56 8 times, 7 goes into 21 3 times. So that one reduces to 8/3. 48 over 16 reduces to 3 over 1. 8/3 is not the same as 3 over 1, is it? So we know, therefore, because the sides are not proportional, have not been cut proportionally, they're not parallel. Okay? All right. Okay, we get some other stuff too. We get this one. Now let's look at this one closely here. This isn't really a triangle thing, but it's sort of like a triangle thing. This is equivalent to the one that we just did. If we go back and take that first, this guy right here, we take this first relationship we had and we say, okay, now what if we take these two sides of the triangle and we've got this point here and we just tilt them up a little bit so they don't actually intersect at that point. They just keep going, and maybe there's another line that passes through R. Okay. So that's where we are with this one. If we've got 3 parallel lines that are cut by 2 transversals, then we know that the 3 parallel lines are going to slice up those 2 transversals proportionally, right? So we get the same kind of a deal going on. We know that the ratio of UW over over WY, right? So sort of like the left to the right segments on top would have to be proportional to the left divided by the right segments on the bottom. Okay? So that's another thing. Okay, we also know the last relationship we get in this section, and this one's just a little bit tricky. This one, in fact, I want to go up here. Yeah. Okay, if some line or some ray bisects an angle in a triangle, right? So you see here that this ray CD has cut this angle C into 2 congruent parts. That's what we mean by bisecting an angle. Cuts it into 2 congruent parts, right? So if it does that, it's going to pass through the opposite side in such a way that it's going to cut the opposite side so that the segments of the opposite side that it's cut into are proportional to the side lengths that go with them. Okay, so in other words, watch this, it's kind of tricky. So the ratio of AD over, oh shoot, yeah. There we go, over DB has to equal the ratio of AC, or CA, whatever you want to call it, over CB. See how that works? Okay. So the ratio of kind of the left to the right segments, right, that the third side's been cut into are going to be proportional to the left to right sides of the triangle. Make sense? That one's a little tougher to see, I think. Okay. There's another way you can slice this one too. You maybe have seen this, but you might notice that all of these can be thought of in two ways. And you can honestly sort of take your pick. The way the theorem goes, it says AD over DB equals CA over CB. That's fine. But we have a property of proportions here that says we can exchange diagonally. So you can also do this. We could say that the left piece of the third side, so the left segment divided by the left side equals the right, equals, there we go, equals the right segment divided by the right side. And that also works, doesn't it? Either way you want to think of it, they both are going to set up a proportion that you can use to solve. Okay, so how do we use this in a problem? Something like, well, we'll come back to it. Here's the, how about one like this first? Okay, we'll do one problem for each of those last two relationships, and then we'll let you guys go work on this stuff. So what about this guy? So in the diagram here, they're telling us that angles 1, 2, and 3 are all congruent. They're telling us the lengths of PQ. So PQ is 9, QR is 15, ST is 11, and they're wanting us to find the length of TU. So let's go ahead and call that, because that's the one we're looking for. Let's call it X. Okay. What can we do? Let's put that away. What can we do with that? This one's a little bit trickier. Okay, good. So, but now before we can do that, though, I want you to tell me why can we do that? Yeah, everybody see that we can do like top to bottom, top to bottom equals top to bottom, because I've got these three lines cut by these two transversals. But that only works if the lines are parallel. Do we know they're parallel? What do you think? They haven't told us directly, but can we show that they're parallel? It told us that angles 1, 2, and 3 are congruent. Let me write that in. Maybe that'll help to just see those congruences. So that angle is congruent to that angle and that angle. Ah, okay, look, those are corresponding angles, aren't they? Right? Let's just focus on the top two. If I've got these two lines cut by a transversal, right? Let's take the top two lines and let's just focus on those for a second. So I've got that line and that line cut by this transversal, right? Well, aren't those just corresponding angles, 1 and 2, right? And don't we know that if corresponding angles are congruent, then the lines are what? Parallel, right? So we know that those two lines are parallel. Now we could do the same thing, right, for the bottom two. Agreed? So we could just focus on the bottom two lines, and corresponding lines, or corresponding angles are congruent, therefore those lines must be parallel. And so now we know that all three lines are parallel to each other, right? And so now we can use that relationship we talked about. Now that we know the lines are all parallel, then we can set up and say, okay, so top to bottom, right? So 9 over 15 equals top to bottom. There's my proportion. Okay? And now that's easy. Now what do we do to solve? Cross multiply. And is there anything we could do to make this simpler before we cross multiply? Yeah, we could reduce that fraction too, couldn't we? Just to make, we don't have to do that, but just to make things simpler, 3 goes into both of those. So I could replace that, instead of 9/15, I could make that what? 3/5, yeah. And now when I cross multiply, it gets a little bit easier. I'm going to get 3x equals 55, right? Divide by 3. And so x equals 55 thirds, whatever that is, right? That make sense? All right, so last one. How about this guy? So this time in the diagram, we're told that the measure of angle CAD, so this angle up here, is congruent to angle DAB. So right there. So we got this triangle ABC, and then doesn't that mean that this angle's been bisected? Okay, so what kind of a proportion can we set up there? And let's not, for a second here, let's not even mess with any of the length. Let's just think of it in terms of the segments, right? So the ratio of, for example, BD over what? So BD over, say, over DC, okay, over DC would equal what? AB, good, okay, AB over AC, okay, good. Right? And we just need to plug in numbers for that stuff so we can hopefully end up solving for something. We're trying to find, by the way, use the given side lengths to find the length of DC. So DC is what we're calling X. That distance from there to there is X, right? Okay, so then what's this going to be? Now 14 is the whole length of this side. BC is 14. How do you know that? Okay, now the angle is bisected. Just because the angle is bisected doesn't mean that the opposite side is. Let me show you an example of why that's true. Right? Let me draw a triangle that's skewed a whole bunch, and you can see that when I bisect the angle, it does not bisect the opposite side. This is probably good to see. So let's take like this triangle right here. Okay. Would you agree that, I'm not going to be able to get this exact, but isn't that about an angle bisector right there? Right, so wouldn't you agree that that angle right there is about congruent to that one? Clearly, this segment on the top is a lot different than that segment on the bottom, right? So would you agree then that even though this one kind of looks like it ought to be cutting that opposite side in half, looks can be deceiving. Doesn't necessarily have to be that way. So we don't know that that's 7, but what could we call it? If we're going to say that we're trying to find CD, so then we're going to call that X. That's the unknown. I know that this whole side is 14. What can I call that top segment right there? 14 minus x. Why not, right? Because I know if the whole thing's 14, and I'm going to take away x of that to get me the length of BD, that's just 14 minus x, right? Tricky. Good. So this part right here, whoops. So this part right here, we can just call 14 minus x. Now that looks a little strange because I've got x's in there for two of my segments, but that's okay. The important thing is I've only got one variable. Only the variable x is going to be involved in my proportion. So when I solve this thing, as long as there's only one variable, I can always solve an equation for a single variable. Sometimes the equations get harder to solve, but I can always solve a single equation for one variable. So now when I plug my stuff in, BD becomes 14 minus x, right? So this one becomes 14 minus x. On the bottom, I've got x. Good. So BC is becoming x. On the other side, we have numbers for both of these, I think, don't we? AB is 9, good, and AC is 15. So all I have to do then is just solve that proportion. And it looks kind of ugly, but how do I always solve proportions? Cross multiply. Right, so let's do that. So if I cross multiply, that cross is going to give me 9x. What about this cross right there? Good, I'm going to have to multiply 15 times the whole quantity, 14 minus x. Right, and now that's just starting to look a lot like some algebra stuff that we know how to do. Right, if we just kind of focus on this algebra, I could distribute the 15, right? And that's going to give me, what, 9x. 15 times 15 is 225, so I got to take 115 away, so that's 210. Minus 15x. Now what? Add 15x, because we want to combine like terms. So we'll add 15x to both sides. So those cancel, and I get, what, 24x equals 210. Last step. Divide by 24. And so I get x equals 210 over 24. Well, I'm not sure how much we can reduce that. I could divide them both by 2 and get 105 over 12. 3 goes into both of those. How do I know 3 goes into both? How do I know 3 goes into both those? Great trick. Gotta know this one. Because the digits add up to numbers that are divisible by 3, don't they? 1 plus 5 is 6, which is divisible by 3, and obviously 12 is divisible by 3. So I can divide them both by 3 and get, oh boy, let's see, 35 over 4, is that right? So, yeah, whatever that is. 8.75. Okay. So there's my answer. Okay, make sense? We good? Okay. There's one more, but I'm not going to do it today. Maybe we'll take a quick look at it tomorrow. All right, let's see if we can now, assuming I can get a laugh.